Welcome back. Today, we're going to follow your smartphone on its invisible, lightning-fast journey to find and connect to a 5G network. It's a process that happens in the blink of an eye, but it's way more complex than you might think.
So, have you ever really thought about it? How does your phone manage to find and latch onto a 5G signal almost instantly? Well, it all kicks off the second you power on your device, with what is basically a very sophisticated, very elegant search party. Okay, so the very first thing your phone needs to do is find a really specific signal. It's called a sync signal that it can lock onto. But here's the catch. Finding that signal in the world of 5G is a whole lot harder than it ever was with 4G.
Right. So in the 4G world, things were simple. The sync signal was always in a known, predictable spot, right in the middle of a channel. Super easy to find. But 5G was built for flexibility, which means its sync signal could be literally anywhere within that channel. And that creates a brand new problem. Where in the world does your phone even start looking? To solve this needle in a haystack problem, 5G introduced a really clever new tool designed to guide the search. And that tool is called the sync raster. You can think of it as a predefined treasure map of frequencies. So instead of having to scan the entire massive channel looking for a signal, your phone just checks the specific locations marked on this map. As you can imagine, this saves a huge amount of time and battery life. And what's really cool is that the map's grid spacing actually changes depending on the frequency band. As you can see, for those super high frequency millimeter wave bands, the steps get much, much wider. This allows the phone to scan those enormous channels way more efficiently. Okay, so your phone's got the map. It's using the sync raster to narrow down the search. Once it gets a lock on one of those potential X marks the spot locations, it starts looking for the treasure itself. And that treasure is something called the Synchronization Signal Block, or SSB.
The best way to think of the SSB is as the network's digital handshake. It's this compact little block of four symbols that contains everything a device needs for that initial hello. It's got the signals for timing and the channel that carries the first batch of critical instructions. And this table really highlights just how smart this design is. See, with 4G LTE, all those similar components were kind of scattered around in different times and places, but 5G packages them all into one single efficient block. It's not only bigger, but it's also much more configurable, which makes the whole process way more streamlined. Okay, but there's another classic 5G challenge, right? The signals, especially at higher frequencies, are very directional. So how does the network make sure that this digital handshake actually reaches your phone? Well, this is where one of 5G's most famous features comes into play: beamforming. The network doesn't just blast the SSB out everywhere. Instead, it sends out a series of narrow beams in different directions. This whole process is called beam sweeping. It's kind of like a lighthouse sweeping its beam across the sea to cover the entire area. And it has to happen incredibly fast. The entire sweep is over and done in just 5 milliseconds. And what's fascinating here is the scale of it all. In the lower frequencies, where signals travel much farther, you only need a handful of beams. But look at millimeter wave. Because those signals are so narrow and directional, the network can sweep up to 64 different beams in a single burst just to make sure it provides full coverage. So let's recap. The beam sweeps out, your phone catches an SSB, and that digital handshake is complete. The phone has synchronized its timing with the network. Now, it needs to read the instructions that are hidden inside. It needs the rulebook. It's this really elegant step-by-step process. The phone decodes a channel inside that SSB to find something called the Master Information Block, or MIB. Now, the MIB itself isn't the final prize. Think of it more like the next clue on the treasure map. The MIB's whole job is to tell the phone exactly where to find the next, more detailed set of instructions, which is called SIB1. And this SIB1, or System Information Block 1, is basically the network's welcome packet. It contains all the critical information, the real rules of the road that the phone needs to follow to get fully connected and operational. This is really the aha moment in the whole process. Because remember, up to this point, all the phone knows is the location of that tiny little SSB. It has no idea how big the actual network channel is. SIB1 is what finally reveals the whole picture. It lays out the channel's precise start and endpoints, which mobile operator it belongs to, whether the phone is even allowed to connect, and how to find any other system info it might need. Okay, so we've walked through the whole dance from start to finish.
But why does this all matter to you? Well, because how this process plays out is actually different depending on which of the two real-world flavors of 5G you happen to connect to. And here's the crucial point. In what's called non-standalone or NSA mode, your phone gets a huge shortcut. It's already connected to 4G LTE, and that LTE connection basically gives it a cheat sheet with most of the instructions. But in a true standalone or SA network, your phone is on its own. There's no LTE to help. It has to perform every single step of that digital handshake we just outlined, all by itself, from scratch.
So there you have it, from a chaotic search in a sea of static to finding a map, performing a digital handshake, and then finally getting the welcome packet, all in a fraction of a second. It's an incredibly complex dance that makes our entire connected world possible.